So the last two areas of this topic that are remaining are percentage yield and atom economy, and we're going to look at percentage yield in this video. So if you turn to page 19 in your notes, we'll have a look at percentage yield, but this is something that you did in fourth form, so this is something that should be very familiar, and we'll go through quite quickly at this stage anyway. The calculations get a little bit more complicated when we use percentage yield in moles type calculations, but today we're just going to simply be calculating percentage yield and use them in basic moles calculations. So where we get this idea of percentage yield from is the fact that not very many reactions will have a 100% conversion to useful products. So percentage yield gives us an idea of the percentage of reactants that have been essentially converted into a useful product. Moles calculations that we've used up to now to calculate the amount of product form is always a hypothetical calculation. It's always, in theory, this is the amount of product that we should produce. But actually, in reality, most cases, we don't get that amount of product. We don't get 100% product that we would expect. We get less product than we expect in a reaction for three main reasons, but there are others. One would be loss of product in separation from the reaction mixture. So if you're carrying out an experiment, maybe in a few different sets of apparatus, so you might start in a beaker and then filter it into a volumetric flask, for example, and then pipette it out into a conical flask. As you go along, you're going to be losing part of your reactants initially, but even when you get to the stage where you are producing your product, if you then want to extract your product from the reaction mixture, so say for example you know that you're left with some of your excess reactants and you want to extract your product, then some of your product may be left behind in the apparatus. So either in transfer between apparatus or in separation of the product from your reaction mixture in your final apparatus, be that a reflux apparatus or even just the likes of a conical flask or beaker. You may also have side reactions happening, so some of the reactants may take part in a different reaction to the desired one. So a reactant may end up reacting with one of your products, and then that's obviously going to lower your yield because some of your reactants are taking place in a reaction that is not producing the product that you want. And the final main reason that would cause a lower than 100% percentage yield would be the likes of reversible reactions that don't go on to completion. So you've got an example there. I've written the equation of the Haber process for the production of ammonia, and you'll be familiar with this reaction as a reversible reaction. You can see from your reversible arrow there, you'll see that some of the products will turn back into reactants, so that would cause a lower than 100% percentage yield. So as I said a bit earlier, the moles calculations that we've been doing up to now, we can get the amount in theory that we would produce based on the mass of reactants used. And this is what we refer to as the theoretical yield. But the mass in grams of the product that we actually get out of the reaction, say for example we were to weigh it at the end, that's what we call the actual yield. And it's from these two values that we get our percentage yield. So the percentage yield is the percentage of the actual yield out of the theoretical yield, and so we can write this equation to represent and calculate the percentage yield. So you calculate it by doing the actual yield divided by the theoretical yield and timesing by 100% to convert it into a percentage. And in some reactions, particularly organic reactions, a 50% yield of product is excellent, and quite often we'd have lower than that. So what I'd like you to do now is to turn over to page 20 and to try exercise 6. Hopefully this shouldn't take you too long at all. It's just a few simple calculations of calculating percentage yield using that equation from page 19. One thing I will say is to check that your units match of actual yield and theoretical yield. So obviously they need to be the same. So if you have your actual yield in grams and your theoretical yield in kilograms, for example, you'll need to convert one or the other so that they match. And just one thing to look out for is to make sure, obviously, your percentage yield will never be greater than 100%, because you can't make more than, in theory, you can make more than you have the reactants to make, in other words. So if you could pause the video now and try exercise 6, and the answers are in the files section of Teams. Once you are finished exercise 6, we will move on with the next part of the topic, so please do come back to the video. So let's continue on with some more percentage yield calculations, and let's introduce moles into those types of calculations. So sometimes you're given the mass of a reactant and asked to calculate the percentage yield from the mass of reactant. And what you need to identify from these types of questions is that it actually involves 2 stages. So number 1 is that we use normal moles calculations to calculate the theoretical yield. So that's the amount in theory that we would produce. And that's basically the type of moles calculations that we've been doing up to now. Then what you do is step number 2 is use the equation above, our percentage yield equation, to calculate the percentage yield. You will be given in the question what the actual yield is. So it's just about spotting that, realizing that that is the actual yield, and then using that for this second stage. Sometimes they split up the question, so they'll ask you, what's the theoretical yield, or sometimes it's referred to as what is the maximum mass, and that all means the same thing. And then they'll ask you to calculate the percentage yield from that, but sometimes they just combine them all together. So you need to be prepared for whatever way they're going to ask you it. So basically how we follow these calculations is we start with the mass of a reactant that we're given. We convert that to the number of moles of the reactant. We use our balancing number ratio to bring that over to give us the number of moles of product. We convert that to the mass of the product using mass equals N times RFM. That gives us our theoretical yield, and then we use our equation for percentage yield to calculate that. And you should write the equation for percentage yield in there just to complete that process. Sometimes I abbreviate it down to AY over TY, but sometimes in the exam they'll ask you to write the equation, so make sure you know it in full as well. So let's go over to the page and have a look at some worked examples of this. So let's look at worked example 1 on page 21. And so we're told here, and we're given the equation for this reaction, that 14.8 grams of butan-1-ol, and that's one of our reactants, and we're told the formula there and the RFM, were converted to 1-bromobutane, again the formula and RFM are given, by refluxing with sodium bromide and concentrated sulfuric acid. Then we're told that 17.8 grams of 1-bromobutane were obtained. What is the percentage yield? So you can see this has all just been put together in one calculation. So one of the most important things with this is that you realise that this is what we call our actual yield, and what we need to work out is our theoretical yield. Okay, so first thing, theoretical yield, second thing, then calculate the percentage yield. So actually we won't use this value of the actual yield until we come to that final calculation of working out the percentage yield. So I've just written out the equation again because I prefer to work underneath the equation, and we just treat this like a normal moles calculation. So what I would do is write down all the information that you know, and also write down the RFM of the values that you will be using, or the formulas that you will be using. So we know we start off with 14.8 grams of butan-1-ol. We haven't been given the mass of our hydrogen bromide, so we don't need to worry about this being a limiting reactant calculation or anything like that. And we're given the mass, the actual yield of our 1-bromobutane. So that's the thing we need to work out. Well, what is the theoretical yield of that substance? And that's essentially our useful product. So I'm going to put my question mark underneath that part of the equation and put grams after it to remind myself I'm working out the mass. I would also write down your RFM values. You don't need to write them of everything, just those 2 things that you're going to be using, especially since they're given to you in the question. So the RFM of this, the butan-1-ol is 74, and the RFM of your 1-bromobutane is 137. So I would write that underneath the equation as well. So what we want to do is work out the mass of our 1-bromobutane, and what we need to do first is convert the mass of our reactant into the number of moles of reactant. So we do that using the equation N equals mass over RFM. Our mass is 14.8. Our RFM is 74. If you had a calculator beside you, that would be helpful. And just type these in as you go along so that you're not just writing in the values, you're actually doing the calculations too. That comes out as 0.2 moles. I want to bring that then over to my 1-bromobutane, and you need to check your ratio, but our ratio here is just 1:1 according to our equation. So that means that in theory we will produce 0.2 moles of our 1-bromobutane. That's the maximum number of moles that we will produce, but as we've been talking about, it's quite common for not all of it to convert into the products, not all of our reactants to convert, or side reactions to happen, or loss of our product when we're separating it from the mixture. So what we want to do at this stage is to convert that number of moles into mass. So we would be doing mass equals N times RFM. Our number of moles is 0.2. Our RFM is 137. And that then comes out as 27.4 grams. So what we want to realise is that this value here is our theoretical yield, and you can see that it's a good bit higher than our actual yield. So that is your theoretical yield. So now we have our actual yield, we have our theoretical yield, so we can use our equation to calculate the percentage yield. So I know you don't have a huge amount of room, but hopefully you can squeeze that in. Again, you might want to abbreviate down to AY over TY, as long as you understand what those abbreviations mean. So percentage yield is actual yield over theoretical yield times by 100%. We're told in the question, and we highlighted it a second ago, that our actual yield is 17.8 grams. Our theoretical yield is 27.4 grams. And we times by 100%. Again, put that into your calculator, and just checking that your units of mass match, so they're both in grams, so that's fine. And that comes out then as 65.0%. And we usually write our answers to 3 significant figures. So hopefully that's straightforward enough. Sometimes it's just about interpreting the question. So use your normal moles calculations to calculate your theoretical yield, and then put that into your equation for percentage yield. So what I'd like you to do at this stage is to pause the video and try worked example 2. So give that a go yourself. Again, don't be thrown off by the complicated names, or if you're not familiar with what reaction is taking place. Remember, it's just the calculations that are important. I would be careful with your RFMs with this, and I will write them down now just to help you out, because that's not really what we're practicing here. It's the style of question. So the RFM of your phenol is 94, and the RFM of your trichlorophenol is 197.5. So if you want to write those in, that's fine. But I'd like you now to pause the video to give this a go yourself. If you're not feeling confident yet, you can just watch the video and watch me going through one more example. But I would encourage you to try this yourself, maybe in pencil. If you get it wrong, that's fine. So pause the video, give this a go, and then replay it when you're ready, and I'll take you through it to make sure you've got the right answer. So let me take you through this. So again, pause the video if you're not finished yet. But you're told here that phenol is converted to trichlorophenol if 488 grams of product are obtained. What you need to identify is that is your actual yield. And I would highlight that in your exam if you were asked a question like this. They're obtained from 250 grams of phenol, so that's our starting mass. Again, we've only been given the mass of 1, so we don't need to worry about this being a reacting mass or a limiting reactant calculation. So I would write the information underneath the equation. So 250 grams of phenol, and our question mark is underneath the trichlorophenol. So first thing we want to do is to convert our mass of reactant to number of moles using the equation N equals mass over RFM. So that's 250 grams over 94, and that comes out as 2.65957 moles. And again, I'd encourage you to keep your answer as accurate as you can throughout the calculation and just round off at the end. So we want to bring that over to our product, which is, you can see, a 1-to-1 ratio. Just be careful, it'll not always be 1-to-1. So in theory, we will get 2.65957 moles of our trichlorophenol. So what we want to do now is to work out our theoretical mass of our product using the equation mass equals N times RFM. That's going to be your 2.65957. Again, if you've kept that number accurate, just keep it in your calculator. Don't start a new calculation. If you have your answer from here, just keep that into your calculator. If there was a ratio to include, you could just type in multiplied by 2 or whatever, but in this case there's not. So just keep that answer and then type in literally multiplied by 197.5. Just keeps your answer nice and accurate as you go along. And that gives us a theoretical mass, a theoretical yield of 525 grams. It's okay to round off at this point because your actual yield has been given to you to 3 significant figures, so it's wise enough to put your theoretical yield in to the same number of significant figures. So that's 525 grams. So then we want to calculate our percentage yield by doing actual yield over theoretical yield. So the actual yield is given to you in the question is 488 grams. The theoretical yield we just worked out from our moles calculation to be 525 grams. That comes out as 92.952%. But again, I would probably round that off to 3 significant figures. That 5 will bring that 9 up to 10 essentially. So that will be 93.0%. So hopefully those worked examples are okay so far, just your basic moles calculations and reacting mass calculations, and then introducing the percentage yield equation. We're going to pause there for now, and we're not going to introduce any added complications like limiting reactants or volumes and densities being given to you. So you can skip past page 22. But if you have time today, or you can leave this to the start of next week if you prefer, but if you have time today, I think it'd be good to practice a couple of those calculations. So to try just examples 1, 2 and 3 from exercise 7, just to give you a bit of practice. None of these involve limiting reactants or anything like that. They're just similar to the ones we've done so far. Question 1 and 2 actually split it up into, first of all, calculate your theoretical yield. Theoretical yield, maximum mass means the same thing. And then part B is calculate your percentage yield. But question 3, it puts it both to those 2 steps together. So just be careful about what's your actual yield and so on. So give questions 1, 2 and 3 a go if you have time now, or you can leave those to start of next week. And then in our next lesson, we'll we'll go back a page and do worked example 3, look at the added complications and complete this exercise. And just to say, the answers to these questions are also in that same document, answers to exercises 6 and 7. So if you want to check your answers to 1, 2 and 3, you don't need to go on any further than that today, and we'll do the rest next time.